Determining a correlation between low temperature and high strain rate in SnapFit application by Nathaniel and Cameron McNany, sponsored by Society of Plastics Engineers, primary contact Dave Rose. Some background on the project is that SnapFits deform at much higher rates than ASTM standards. Standard testing methods do not accommodate for this material response using typical stress strain curves. So since these high strain rates and low temperature are not represented in these stress strain curves, additional testing needs to be performed so designers know what guidelines and recommendations to design for SnapFit application. The project mission statement is to determine stress strain correlation at high deformation rate and low temperature. Low temperature testing is commonly used and additional data is published and easily accessible. So using this low temperature data as an early estimation of this high deformation rate that these SnapFits deform at can be used for these designers to design and make guidelines to ensure that the SnapFit can uphold and not fail during application. So the selected materials are commonly used in SnapFit application. We did 2 semicrystalline, a polypropylene and a PBT, and 2 amorphous, an ABS and a polycarbonate. Should be noted that an ABS is a tear polymer of acrylonitrile, butadiene, and styrene. Using a different composition and percentage of these monomers can give different reactions, how the ABS grades will react to the rate sensitivity.
For our mechanical testing, we chose to use the new Angstrom 34TM load frame we received in the plastics processing lab. We also decided to use 3-point bending or flexural testing as our main method of determining the flexural properties, as most cantilever beams deform in this way. We used ASTM D790 to evaluate the flexural properties, and using that, we also varied our strain rates as shown in the equations below, and our environmental temperature using the environment chamber as shown here. And we also gathered temperature data using the environment chamber and an test sample readout. So our significant results in polypropylene, as we increased our rate of testing, we saw a 34% increase in our material modulus. And as we lowered our test temperature, we saw a 27% increase. And these testing methods were nearly similar in terms of modulus. For ABS, as we increased our strain rate, we saw a 6% increase in our material modulus. And as we decreased our test temperature, we saw again a 6% increase in modulus. In terms of yield behavior, both an ABS and PBT saw an increase in our yield stress and yield strain as we increased in strain rate, and was not necessarily representative of a low temperature test. So in conclusion, the strain rate effects are material dependent, as shown by polypropylene, ABS, and PBT all behaving differently and with different magnitudes of change. And in general, TG is a relative indication of the material's chain flexibility and possibly the temperature and rate sensitivity of each material.